This is FRQ 8-1. Circular satellite orbit becomes a large ellipse. So a lot of these Unit 3 QQTs are going to discuss orbits that change in some way, whether they get further from the planet, closer to the planet, become an ellipse, and discuss things in that way. So my hope is that as we go through this, some of the fundamental stuff is going to get a little bit easier. So you can see here that a satellite is traveling around Earth in a circular orbit at a constant speed, v, and a constant distance, d, from Earth's surface as shown above. An identical satellite is set into orbit around a new planet. The new planet has the same radius of Earth, but is significantly more massive than Earth. The satellite orbits are the same distance from the surface of the new planet. So part A says, is the speed of the satellite orbiting the new planet greater than, less than, or the same speed as the satellite orbiting Earth? So, to find the speed of an orbit, remember we set the gravitational force equal to mv squared over r, because it's the gravity of the planet that keeps the satellite in orbit. So remember Newton's universal gravitational law, g times the product of the masses. For this, I like to use little m for the satellite or whatever is orbiting, and we use m for the planet. Okay, so I'm going to say g little m big M over r squared equals a centripetal force, right? So it's mv squared over r. So to find the speed of the planet, speed of the satellite around this planet, we can cancel out the mass of the satellite, which hopefully is at least sounds familiar to you, and we get the square root of big G, the mass of the planet, over r. Okay, now we do have to, in real life, think about this r a little bit here, because we've got to add the radius of the planet to the altitude, but in this problem that's not coming into play, so we won't worry about that too much because the radius of the new planet is actually equal to the radius of the old planet. So whatever that distance is, it doesn't matter. However, the new mass is larger than the old mass. So we can't actually do a factor of change problem here, but we can do what I like to call a qualitative factor of change, looking at this expression for v, right? Well, for the new planet, g is going to stay the same, m is going to get a lot larger, and r is going to stay the same. So the new velocity is going to be larger or faster. All right, so that's all we need to say for part A. We don't need to say how much faster, and in fact, we can't. So for part A, 2 points. 1 point for saying that the new speed is larger, and the other point for relating the gravitational force to mv squared over r. Remember, that's our key for getting the speed of an object in orbit, equating the gravitational force to a centripetal force. That's part A. For part B, students find this equation on the internet to describe circular orbits in general. The equation may or may not be correct. So we have m as the mass of the planet, t is the orbital period, r is the distance from the planet's center to the satellite, and c is a constant. So part B asks if this equation is consistent with our reasoning in part A. So what I said in part A is if you have a heavier planet with the same radius, the new velocity is going to be larger. Let's see what happens here. If I have a heavier planet, that means my mass goes up, everything else stays the same. The radius stays the same. Well, if all of this is going to equal a constant, if m increases, then t must decrease, okay? Since the product of m and t squared must remain constant, if m increases, then t must decrease. Now, if the period decreases, that means it gets around that 2 pi r faster, so that means our velocity is faster. So in fact, it is consistent with what we said in part A. So what do we get? We get 1 point for a correct answer that shows functional dependence. So when I said since the product of m and t squared has to equal c, if m increases, t decreases. That's our functional dependence. Then 1 point for actually getting the functional dependence correct. And then 1 point for explaining that if the period decreases, the velocity increases. So again, you get that first point just for going to the formula, just for trying to use the formula in some way to justify your answer. You get that point, and then you get another point for actually doing it correctly. So you get a little bit of a bonus there. That's part B. Part C is one of those parts that we're going to have to actually read, okay? The original orbital satellite is orbiting clockwise around Earth. When the satellite is at point A in the figure, it fires a thruster, which exerts a force on the satellite for a short time, modifying the orbital path. The dashed line in the figure shows the original orbit. The solid line shows the modified orbit. So we started out as a circle, we're going to the ellipse. Part C says, consider the force exerted by the thruster at point A that modifies the satellite's orbit. From the dashed line original to the solid line new orbit. Was the force exerted in the same direction as, in the opposite direction of, or perpendicular to the satellite's velocity at point A? And of course, we're going to describe our answer. So the answer is here in the same direction, okay? In the same direction as the object's motion. So if it's moving clockwise at A, it's really moving up, if you will, okay? So the thruster then fired, well, it fired backwards, but the force on the satellite would be up, okay? The force exerted by the thruster, so the force is going to be in the same direction. And so we know this because we got farther from the planet, okay? And it increased the orbit. We got further from the planet, so in order to do that, we had to add some energy there. So let's see. The points there are 1 point for one point for staying in the same direction, and 1 point for relating the direction of the force to a change in speed. Okay, and we had to speed it up to get it out to that orbit. So that's part C. Okay, D, E, F, and G are the hopefully by now familiar student 1, student 2. Students are discussing the satellite in its new clockwise elliptical orbit as it travels from point A to point B. So it's important from its closest point to its farthest point. Student 1 says the satellite is moving faster at point A because the satellite's angular momentum is greater at point A than at point B. Now, student 1 is right on the first statement. The satellite is moving faster at point A, and we learned that when we talked about Kepler's second law and conservation of angular momentum, which leads us into the second statement, which is wrong. The satellite's angular momentum is greater at point A than point B. Well, it's the same at both points, so the second statement is wrong. Let's move on to student 2. Student 2 says the satellite's moving faster at point B because the gravitational potential energy of the satellite Earth system is higher at point B than at point A. So there is more gravitational potential energy at point B. So the second statement is correct. Okay, there is more gravitational potential energy at point B, but the satellite's not moving faster at point B. In fact, it's moving slower at point B. The satellite doesn't move fast because the gravitational potential energy is stronger. The satellite moves faster because the kinetic energy is higher. So there are the answers for D, E, F, and G, 1 point each, and on to question H. So in H and I, we're going to look at the energy versus position, I suppose, graphs for this orbit. So part H says, which of the following graphs best represents the magnitude of the gravitational field at the location of the satellite as it orbits? So you might notice that graph 1 is wrong off the bat there because magnitude is always positive. So it can't be that. You probably realize that the magnitude of the gravitational field... Sorry, I got interrupted there. The magnitude of the gravitational field at the location of the satellite as it orbits. So the answer here is graph number 2. So since we're closer to the planet at point A, the field is stronger here. Now, I got caught the first time trying to figure out where the planet had more gravitational potential energy, which is a subtly different question. But remember, the field of Earth or any other planet is going to be stronger closer. Not that we're holding more energy there, but the field is stronger closer to the planet. So you see that the field is stronger at point A and then dips down at point B. So graph 2 is the right answer there. We get 1 point for saying that graph 2 is the right answer, and then relating the field strength to distance by saying that the field is stronger closer to the Earth. You get that point. And we kind of got a little bit hosed this year not doing electric field, because we can make a lot of nice comparisons to electric field and gravitational field, but it should make enough sense to you that the field is closer, stronger to the Earth. So 2 points for part H. Now part I says, which of the above graphs represents the total mechanical energy of the Earth satellite system as it orbits? So hopefully it kind of clicks. Well, the mechanical energy is constant, right? It fluctuates back and forth, but it's constant. So that should send you over towards graph 1, which might panic you for a minute because you're like, wait a second, it's negative. But remember, when we calculated total mechanical energy of orbiting objects, we got negative answers because the gravitational field is always negative. And then even if the kinetic energy is positive, we can still get a negative answer there. So you get 1 point for indicating that graph 1 is correct, and 1 point for explaining that mechanical energy is constant because there are no external forces. So that's 8-1.